Okay, so now what we're going to do is if we've built our own data structure, we've worked within a predefined data structure, let's step back. Let's say more specifically, we've built our own data tree, we've worked within a predefined data tree, we've manipulated a data tree, maintaining certain elements and removing others within the path structure. Now we're going to talk about how we can use data trees to organize elements by creating our own custom hierarchy, right? So there are times when we have a collection of elements, they're all on one list, and we want to organize them in a way that makes sense for what we're doing. So the geometry type that we're going to use within this exercise is going to be meshes, right? Meshes are defined by a set of points, which we call vertices, arranged into a basic collection of elements called faces, right? So we have each vertex here, and the connection between those vertices is an edge, and the connection across multiple vertices results in a face that's either a quad or a tri. Rhino has limitations to those two types of mesh faces, right? Some of the additional properties we can gather from the faces from the mesh are faces, edges, vertices, how those vertices are connected. That's our topology. And typically meshes are understood as faceted geometries, and they're nice because they can help us easily define built elements, parts that compose something else that we're going to make. We can also use them to more loosely define or approximate a curving surface. Right, so the things that describe meshes, right, the elements, are really understood through their connectivity and geometry. The connectivity is in what way are these meshes defined as a collection of connected elements. So this quad is defined as 3, 6, 4, 1, right? That connectivity also helps us define through topology the direction, right? So how many relationships across the vertices and edges are there? And that's the topology, right? So these two meshes, if we see them side by side, are the same relative to how they are connected, but they are different relative to their shape. So what we understand as kind of shape is different, what we see, but their topology is consistent. All right, so we're going to use the decomposed path again, but we're going to use it as a way to then recompose a new path that is customized for our situation and use that to replace a certain set of branches within a tree structure, right? And this is a little bit more complex because we can do this kind of very straightforwardly. We can say every path is going to get a new name, or you can do you can create paths, new paths by masks, or kind of query strings where you're saying anything can be in location D, but only one can be in location C within the path structure. So we're going to focus on the basics, but just to let you know that there are some more complex relationships you can define within your replace branches mask. There's a list of these are in the help for this object, but asterisk is a wildcard. It's any number of allowed digits. A placeholder is a particular slot that you want to let be anything, but has to be in that slot, etc., etc. All right, so let's go ahead and take a look at the next exercise in Rhino. What we're going to be doing here is using data trees to organize elements. And we said we're going to be working with meshes, right? So let's go ahead and look under the Mesh tab at the Triangulation subtab. We're going to use a Delaunay mesh. This is a simple way to create a mesh very quickly based on a collection of points. It's a kind of planar projection, trying to create simple triangles through a collection of points. And for our cases, for our case in this exercise, let's assume that we have random points, right? Or that our specific points that we would use in our creative application are going to come from somewhere else, and for a placeholder for now, we'll go ahead and use populate 2D for some random points. Okay, so this asks for a rectangle to define the points, and we can say how many we want, how many points, and what the seed is for the randomization, and also P allows us to use a pre-existing population, which we don't need. So let's say the rectangle will stay as default. The number of points to add will be 100. And actually, let's go ahead and create a slider for that. We want more points, so let's say that there has to be a minimum here on the slider of 50. We can use 100 as the current value and go up to 250. That way we can have more or less points in our collection. All right, and the other thing we want to do is we want to leave this as the predefined rectangle, but let's right-click and say extract parameter. That pulls that locally defined value out of the object and has it here so we can use it elsewhere. And this is going to be our input rectangle. All right, so with this set of points, if we connect this into the P input, we'll see a mesh created. Now I can't see the edges in my display. You might be able to, but if you can't, we want to make sure that you go to display preview mesh edges. Right? So now we can see the connectivity of each face within the collection of points, and again it's trying to create the simplest set of triangles that will create a mesh through all the points that we've supplied. Right? So let's take a look at what we get from this. Right? This is a collection of mesh. This is a mesh that is composed of multiple mesh faces, but we don't know how these faces are organized. Right? Let's assume that what we want to do is take this set of mesh triangles, and we want to make this mesh out of some physical material, like maybe we're going to laser cut all of these mesh triangles individually and glue them up together. The Delaunay will work with 3D points also, so if you want to try an alternative option while we're working on this exercise, you could include the populate 3D as your alternative, right, to bounce between, so it will create a triangulated mesh in a similar way, but it's connecting through the points that have some Z height. Okay, so I'm going to stick with this, but I'll leave this in the file as an alternative for you to reference. Okay. And the idea here is that we need to find out how these things are organized, right? So let's go to the Mesh tab. We have no idea how they're ordered, and if we wanted to laser cut each one, it might be relatively easy to get the triangles to be isolated from each other and laid out for laser cutting, but it's not going to be clear in terms of the numbering strategy on what is what, right? So we want a more clear ordering strategy for these mesh faces. All right, so let's go ahead and under the Mesh tab, let's see if we can't find something that will give us the face centroids, which we have an option here called face normals. So if I plug my mesh into this, this will give me the point and vector at every mesh face center. Right? So this is the centroid of this mesh face, right? And if we plug the result of these center points into a point list object, we can see how they're organized. Turn some previews off here. Go to top view. We now see it's ordering all of the faces by their location within the X direction. And then there's once it gets to the edge, it kind of bounces around a little bit based on probably some of those more funky triangles that are at the edge. All right, so generally we have an organizational scheme for this, but it's not very clear. So what we want to do is we want to make a very clear organizational scheme for all of these mesh triangles. All right, so what we're going to do is we're going to relate them to something else, right? We could organize them based on their Y or their X, But let's say that we want to organize them relative to a point that exists on this rectangle here, right? That's the original rectangle that defines the population 2D. So let's go to curve and analysis and use our point on curve object. Connect that up, and now we can move a point along the curve and define what the organizational scheme will be relative to its location in space. So I'll put it over here like at the corner, something like that. That sounds good. Okay, great. So now what we want to do is we want to reorder all of the mesh faces based on their location or distance to this point, right? So what we're going to do is we have to get the mesh faces, and right now we just have one mesh. It says 140 vertices with 263 faces. We need to get each one of those faces isolated. So what we're going to do is we're going to decompose the mesh, which is under the Mesh Analysis tab. So take the mesh, decompose it. Now I have all of the vertices, faces, if I have vertex colors and vertex normals, all isolated into different outputs from this object, right? So here are my faces, and this is just describing the connection of the vertices. So if I take the faces apart, if I go to Analysis, Face Vertices, this will allow me to access A, B, and C separately for each one of the mesh faces. Now, if we graphed, right now it's giving me a list of all the first index values for all the faces. But if I graphed the F input, and let's try this locally now, because we've been doing it with the graphed object, but all inputs have this option for grafting here. We're going to graph the faces, and now each A, each B, and each C is on its own list, right? Because the data structure has grown. All right. So let's bring those three back together onto one list. All right. So this is a merge object from sets tree. Here's my merge right there. All right. So I'm going to go A, B, and then zoom in, C, and then I'm going to remove D4. I don't need that. This automatically will resize when you're adding inputs to it. And if you want to change the number of inputs, you zoom in here closer and you'll have these options. Okay, so now we have each one of our collection of vertices as its own list within a data tree. Perfect. Well, what that will allow us to do is if we ask for those points based on their item, so list item, this is sets list item. All right, I'll choose them. Now I have all of the face vertices organized on their own tree branch, and then I can create my polyline from curve spline. Polyline. And now I have each one of these as a triangle, right? And they're lines now. So now I can work with these and shuffle them around as I see fit, right? And they're each on their own path right now, which is perfect. All right, so I'm going to save this before we get too much farther along. This is 1-3. Okay. Now the trick is that we need to compare them to get rid of this stuff, to their relationship to this point, right? So we're going to compare the polyline to the point, and then based on that, we're going to resort our polylines, all right? So what we're going to do is first, before we go any further, we've got our polylines. Now we want to go back through and make sure that our data tree is nice and tidy, right? So before we start doing our next chunk of the file, let's go to sets tree, and let's simplify it, right? So what was A, B, C, D now will become A, and there's no overlapping branches. That's great. All right. And then from there, we're going to do the rest of our file, right? The first step is we need to get the center point of every polyline right here. So I'm going to go to my curve tab, and there's an object here called polygon center, which gives me that very easily. All right, so here's my organized, well-organized polylines. Here are my corresponding center points. It gives you both the vertex centroid as well as the edge centroid. For our purposes, either one will work. And what we want to do is test the distance between this point here and this point here, right? So I'm going to go to the vector point tab, grab the distance object, and from this center to that point, I'll now have a distance value for each one of the polylines, which is here, right? If I check out the result on a panel, we'll see that we have here a bunch of different distance values, right? So that's going to help me reorganize things based on that distance value.